So, what we want to do next is we want to centralize our studies around around a particular kind of problem. We're kind of going to shift the focus of the camera away from the computer and towards the problem that the computer is trying to solve. And so what we want to talk about the kinds of computational problems which we might want to solve. And there's many types, right? There's lots of different kinds of things you might want to do on paper. And a few examples, not at all exhaustive, are, well, there's function problems. So, you know, calculating a thing, right? You know, given x, find, I don't know, the square root of x, or x squared, or a solution to an equation. You can even think of that as a function problem. You can kind of think of all of the kinds of problems as function problems, but, you know, this is kind of the obvious thing, right? Given two numbers, add them. That's kind of you can think of that as a function problem, where the function is like kind of it's plus, and it takes two inputs, and it spits out an output, right? So that's one kind of computational problem. Another kind of computational problem would be optimization problems, and these are pretty popular. So stuff like, you know, basically, you know, find a maximal or minimal thing subject to some condition. So that's a little abstract. Maybe the kind of most famous example of an optimization problem is the traveling salesman problem. So an example, I'm not going to write it out in a detail. Maybe I'll just explain the traveling salesman problem. So in the traveling salesman problem, just to give you an example of an optimization problem, you're essentially given a graph, which means you're given a set of vertices, and it's a connected graph. There's a way to get from any one vertex to every other vertex. So let me try to make that, you know, representative. There's, you know, I can get anywhere. Let's just leave it at this. And specifically, it's not just a graph, it's a weighted graph. So this is node 1, I'll say. This is node 2. This is 3, 4, 5, 6. We've got like kind of 6 vertices. And every single one of these edges that connects them has a weight. So maybe this is 10, and this is 13, and this is 5, and this is 6. And you can think of the weights as distances. Essentially, you can kind of think of this 10 as saying you can go straight from 1 to 2, and that is a 10-mile distance. You can go straight from 1 to 3, and that's a 13-mile distance, etc. It doesn't have to be distance. It could be anything. But essentially, you have a cost from getting to 1 from 2. And the idea is to visit every vertex at a minimal cost. So, you know, what's the shortest path I can take that gets me to everything? That's the traveling salesman problem. He wants to get to every house, and he wants to get to as many houses as possible in a day, right? This is a very difficult problem, but this is an example of an optimization problem. Optimize the circuit that goes through all of the vertices. So that's an example of an optimization problem, and it's another example of something you might want to do on paper. But then there's the most important kind of problem, and in some sense, the fundamental problems. You know, in some sense, like in a kind of, I don't know, philosophical, moral sense, I think you'll agree with me that this is really the most important kind of problem, and these are the decision problems. And I think that we're in a unique vantage point where we can understand better than probably your average computer science major why these are really the important kinds of problems to consider. I mean, that's not to say these aren't important problems to consider, but these are kind of simple. They're like the kind of like atomic form of a computational task, and I'll explain why. But before I do that, I should say, you know, the task is basically, you know, decide yes or no for something, for some input. That's it. So it's pretty basic. So examples, there's lots and lots and lots of examples. You can, and I'm going to give these problems names because, again, I want to start to emphasize that in computability theory, the objects of study are problems. You know, in number theory, you study numbers. In topology, you study spaces. In computability theory, problems are your objects of interest. And so we are going to start viewing problems as not just problems to solve, but also mathematical objects that exist in a space, because they are. But some examples of these are, maybe I'll start with the factoring problem, and I'll call it I'll just call it factoring. So the factoring problem as a decision problem is given an integer x, decide if it has a non-trivial factor. Right? So if you're given the number 7, then the answer is no. If you're given the number 11, then the answer is still no. If you're given 12, then the answer is yes, right? If there's a number that divides the integer that isn't 1 or itself, that's what you want to decide, yes or no to that. Another example would be Palindrome. These are just the ones that come to my mind immediately when I think about decision problems. Which is given a string, does it read the same forward and backward? So that's another example. And I think to explain the importance of decision problems, I should probably give you one more example that isn't really the same thing, right? Everything we've been talking about, and I should probably emphasize that for the rest of these videos, we're going to be very focused on specifically pen and paper computation. We're sort of done talking about physical computation. I brought it up for broadening our perspective, but the focus of the rest of these talks is going to be on pen and paper Turing machine computation. So keep that in mind. But an example of a physical decision problem is a thermostat is in cooling mode. It gets an input. It has a desired temperature. And continually reads temp from the environment. So it's getting input from the environment. It's getting the temperature. And what does it need to decide to do? It needs to decide. I'm getting sick of writing, so it needs to decide whether or not to turn on the fan. It needs to make a decision. And so I think that this example should probably sink in a little bit in terms of why I can sort of think of decision problems as the atomic form of computation as a philosophical concept. Because again, think about the model that Turing gave us, which is that we have these boxes, right? We've got the control, and we've got the store, and we've got the executive unit. And the control reads from the environment, and that it has to decide to do something. It decides to do something. Now, it might make multiple decisions. It might have to decide. It might have to ask many yes or no questions about whatever it's reading from the environment in order to come to a conclusion. So there might be multiple decision problems implicit to a computation, but nonetheless, it kind of all breaks down to a set of decisions that need to be made. So let me kind of put it like that. Any computation, in principle, there's no way to really prove this, breaks down into a bunch of decision problems, a bunch of decisions to make. So thus, the study of decision problems is sort of, in microcosm, the study of computability theory in general. And so we're going to focus very much on decision problems, and we're going to view them as mathematical objects. And so I think I'll stop the video and move on, and we'll continue talking about decision problems in the next one.